So I'm just waiting for people to log on. Let's see, is there someone named Abal? Wait, you're muted. I just need to know whether Amal is your first name or your last name for attendance.
Amal is my first name.
All right, sorry, and your last name?
Mia Wiboasuni is a long last name.
No, spell it, please.
Miaoui hyphenates Bouazzouny.
Okay, thank you.
You're welcome.
Okay, well, let me start slowly today because it's the first day of class, and maybe that some people still need to figure out how to log on through Zoom. So this is Math 424 Pde, which means partial differential equations. So a lot of the information about the course is posted on the website, and I also emailed it out to everyone last night. So let me just start by saying, what's the subject of the course? Let's see. So a differential equation is an equation where the unknown is not a number, but it's a function. And so it can involve a variable x, y, z, other variables, t, and so forth. And the equation involves u and its derivatives. So it's called a differential equation because there's an unknown function, and the equation says something about the function u and its derivatives. So an ordinary differential equation, or ODE, is a differential equation in which the unknown function u is a function of just one variable. So u might be a function of x, or a function of t, or any other variable we want to choose. So an example of an ordinary differential equation might be du dx equals 10x, or x du dx equals x plus 1u. So these are equations where the unknown is the function u, and the derivative somehow appears inside the equation. Okay, that's an ordinary differential equation. A partial differential equation, or Pde, is an equation where the unknown function u is a function of two or more variables. And again, it doesn't matter what the variables are called. U might be a function of x and y, or u might be a function of x and t, or u might be a function of x, y, and z, or u might be a function of x, y, z, and t, and so on. I mean, it can be a million variables. And when we can't talk about the derivative of a function of several variables, but you have the partial derivatives. So the Pde involves partial derivatives of u. So you might have ux, which means the partial of u with respect to x, or ut, which is the partial of u with respect to t, or uxx, which is the second derivative, the partial of u with respect to x twice, or uxy, which is the second partial of u with respect to x and y, and so on. Right? So a Pde involves partial derivatives of the function. So you might have, for example, the equation ut equals uxx. This means we want to find a function u of x and t where the partial derivative of u with respect to t is equal to the second partial derivative of u with respect to x squared, with respect to x. Differentiate u with respect to x twice. And usually I won't write my partial derivatives in this form. Usually I'll just write them like this. And that's the way you'll find it in the textbook. Okay. Now, a course in ordinary differential equations is not a prerequisite for this course. But what is a prerequisite certainly is calculus. And part of Calc 2, second semester calculus at Lehman, involves a little bit about ordinary differential equations. And I'm going to review that this morning. let me just say a little bit about how partial differential equations are classified. So we have, first of all, so this is classifying PDEs. So the first and simplest thing is just how many variables are there? The number of variables. So if you have the differential equation ut equals uxx, there are two variables, x and t. If you have ut equals uxx plus uyy, these are all famous equations. This has three variables, x, y, and t, and so forth. So the first thing you do when you want to understand a differential equation is the first thing you ask is the first thing you look for is how many variables are we talking about? There have to be at least two, otherwise it's not a partial differential equation, it's just an ordinary differential equation. So PDE will have two or more variables, and we want to check how many variables there are. The second classification has to do with the order of the PDE. So if you have u sub x or uy or ut, for example, these are first derivatives. So these are partial derivatives of order 1. If you have uxx or uxt, these are second derivatives. These are partial derivatives of order 2. If you have uxx or uxyz, these have order 3. The order of a partial differential equation is the order of the highest partial derivative that occurs. So for example, if we look at the partial differential equation ut equals uxx, this has order 1, this term has order 2, so the equation itself has order 2. It's the largest of the orders of any of these partial derivatives. Okay. Okay. What else can we say? Well, there are linear and nonlinear partial differential equations. An equation is linear if it is of the form. So you might have second derivatives of your function and first derivatives and the function itself. And these aren't multiplied together. You might have something a times uxx, b times uxy, c times uyy, d times this, e times this, f times this equals g. So where a, b, c, d, e, f, and g are functions of x and y, but they don't involve u. They could be constants. So you could have a differential equation with constant coefficients. You could have an equation like 3uxx plus 2uxy plus 7u equals 0. So this is a linear differential equation, and a lot of these functions, a, b, c, d, e, f, and g, and this are 0. And the ones that are not, you have a 3, a 2, and a 7. But this is a linear differential equation. So a linear differential equation, let's say of the second order, If it's of the second order, it involves at most the second partial derivatives. So you have the function u. Here I'm just looking at a function of two variables. You have a function u. You have the first partial derivatives, ux and uy, and you have the second partial derivatives, uxx, uxy, and uyy. And their coefficients in the equations are functions of x and y, but they don't involve a u. So such an equation is linear. And what is a nonlinear equation? An equation is a partial differential equation, is nonlinear if it is not linear. That's easy. So if you take the differential equation u times uxx plus 7uy equals sine of xy, that's a nonlinear partial differential equation. Why is it nonlinear? Because here I have u times uxx. So I have a product of partial derivatives involving u. So this is a nonlinear differential equation. Okay. Most of the time, we're going to focus on second order linear differential, second order equations in two variables. So typically, the most general, typically, if we have a linear second order differential equation, it's going to look like this. So a linear second order PDE is homogeneous if the right-hand side is 0, and non-homogeneous if the right-hand side is different from 0. So a homogeneous differential equation has g equals 0. This is just like what you learned in pre-calculus when you were looking at systems of linear equations. If you have a system of linear equations like 7x plus 2y equals 0, 3x minus 8y equals 0, this system was called homogeneous because the right-hand sides were 0. And if you had the system 7x plus 2y equals 1 and 3x minus 8y equals minus 7, this system was called non-homogeneous. So this is a kind of terminology that you've certainly seen before. Right? So second order differential equation is homogeneous if the right-hand side is 0. Not homogeneous otherwise. Okay. Are there any questions about that so far? Okay. Now, in the classification of PDEs, there is of a second order PDE. We do the following. So this is our 5th classification category. So this is the classification for second order linear partial differential equations. You have an equation that looks like A uxx plus b uxy. Oops. This is b. A and b are functions, not necessarily constants. A, b, uxy plus cyy plus dux plus e uy plus f times u equals g. So this is our Second order, because it involves second partial derivatives. Linear, because it's linear in U and its partial derivatives. Partial differential equation. And this is really determined, the behavior of what solutions look like are really determined by the second order part. Now, this is going to be related to what you learned again in elementary school or high school or somewhere when you solved a quadratic equation. If you had a quadratic equation, ax squared plus bx plus c equals 0, you looked at what's called the discriminant, b squared minus 4ac. And that's what we look at here. Forget these terms for the moment. Just look at the coefficients of the second order partial derivatives in this equation. A is the coefficient of uxx, b is the coefficient of the mixed partial uxy, and c is the coefficient of this is u, the second derivative of u with respect to y. Look at b squared minus 4ac. And there are three possibilities. It could be equal to 0, could be greater than 0, or could be less than 0. And we classify second order linear differential equations by the value of b squared minus 4ac. If this equals 0, the equation is called parabolic. If it's positive, it's called hyperbolic. And if it's negative, it's called elliptic. And we will see it throughout this course that there are completely different properties of parabolic, hyperbolic, and elliptic partial differential equations. Now you can ask, where do these names come from? Because you know what a parabola looks like. That's a parabola. You know what an ellipse looks like. Sorry, an ellipse. And you know what a hyperbola looks like. So maybe I'll spend just a minute or two to try to see the connection between this b squared minus 4ac and these three geometrical words, right? Let's see. Let's see how we might do this. Suppose we had an equation ax squared plus bxy plus cy squared equals, I'll say 1. Okay. And we want to graph this equation. Well, okay, so there you are sitting in the privacy of wherever you are, at home or wherever, and you should have some paper and pencil handy. So why don't you try to graph this equation and see how the shape of the graph is connected to the value of b squared minus 4ac. That might be a useful exercise. So before I go ahead and do it, why don't you do it? see. One thing you might do to make it a little bit easier is to complete the square. So if you complete the square, let's see, I could multiply through by a. And then if I look at this, how do I complete the square? A squared x squared plus abxy plus b squared over 4y squared minus b squared over 4y squared plus acy squared equals a. So I just added and subtracted the same thing, and I did that because then this term is ax plus b over 2y squared minus, what do I have here? If I factor out a y squared over 4, I get b squared minus 4ac y squared over 4 equals a. So let me change variables just to make this a little bit easier. Suppose I let u be ax plus b over 2y and v equal to y over 2. So then what I get is u squared minus this number, b squared minus 4ac, v squared equals a. So just to make things slightly easier, suppose I let delta be this number b squared minus 4ac. Or maybe I should call it d for the discriminant. So u squared minus dv squared equals a. And just for make things a little bit less complicated, let's say a is non-zero. So what does the graph of this look like? Suppose so I have the equation u squared minus dv squared equals something a different from 0, and d is b squared minus 4ac. Well, if d is greater than 0, u squared minus dv squared equals a is a hyperbola. I mean, that's exactly the equation of a hyperbola. Right? This is u axis and v axis. When v is 0, u is square root of a. Let's just say a is positive. So when u is 0, when v is 0, u is plus or minus the square root of a. And as v gets bigger and bigger and bigger, I mean, you just get a hyperbola that looks like that. Right? So if this isn't familiar to you, then really you need to go back and review some, whatever it is, wherever you learn about these things, but it's just a hyperbola if d is positive. What about if d is negative? So then you have u squared minus d, that's plus, minus d is positive, v squared equals a. This is a positive number. So, for example, when v is 0, this is plus or minus the square root of a. When u is 0, this is positive. So, so v is plus or minus the square root of a over minus d. Those are the x and y intercepts. And you get this ellipse. So if this discriminant d is positive, this quadratic has the shape of a hyperbola. If the discriminant is negative, this quadratic has the shape of an ellipse. What happens if d is 0? That's a little bit more complicated, perhaps. So suppose that d, which is b squared minus 4ac, is 0. So what does that mean? That means that b squared equals 4ac. So if we're looking at the equation ax squared plus bxy plus cy squared equals 0, when we complete the square, let's see, what did we get? We get let's see. When we completed the square, we got ax plus b over 2y squared minus b squared minus 4ac, y squared over 4 equals a, but this was 0. So this is ax plus b over 2y all squared equals a. Let's see. I want to show that I get a parabola, but somehow I'm stuck. So why is this? So I don't want to spend time now because I can't figure out how to do it. So I will come back to that on Monday. So what is the problem? I'm kind of puzzled. So we take this ax squared plus bxy plus cy squared. We take our partial differential equation. We look at b squared minus 4ac. And this came up just from the way we were classifying these equations. And I wanted to explain the class where the words come from, really. So here's the second order equation. We look at b squared minus 4ac. If it's positive, we call the equation hyperbolic. And that's because when we look at the corresponding quadratic equation, the graph's a hyperbola. If b squared minus 4ac is negative, when we look at the corresponding quadratic equation, the graph is an ellipse. And when b squared minus 4ac equals 0, we call that partial differential equation parabolic, and it should be that we get a parabola as the shape of the corresponding quadratic. But I'll figure that out and talk about that again on Monday. Okay. So if you look at our textbook, which has several virtues, one is it's a Dover paperback, so it only costs less than $20, as opposed to most textbooks in partial differential equations, which cost more than $120. But we've just covered lesson 1, and but I also, which is what I wanted to do today, but I also want to just review something about ordinary differential equations from Calculus 2. Math 176, says Lehman. So there were 2 types of ordinary differential equations that were considered. So in this ordinary differential equation, y is a function of x, and a typical differential equation would be of the form dy dx equals some constant times x. Find y. Find some function y equals f of x that solves this differential equation. And sorry, that's too easy. Dy dx, sorry, well, maybe I should just solve it just to make it sure that maybe the simplest differential equation, first order linear differential equation, would be dy dx is some function of x. And what is the solution? Well, this says find a function whose derivative is f of x. The solution is the antiderivative. Y is equal to the integral of f of x dx. That's the definition of the integrals, the antiderivative. So if you have a differential equation, dy dx equals f of x, the solution is the integral. And sometimes, in addition, you have an initial condition, like maybe f at some value a is equal to b. So then, in addition to finding the general solution, this would be the general solution. You want the particular solution where when x is equal to a, y is equal to b. So for example, suppose dy dx is equal to x squared, and we're told we want the solution where f of 0 is equal to 5. So what does that say? Well, the general solution is y is the integral of x squared dx. That's 1/3 x squared plus a constant. And at x equals 0, you get y is 1/3 0 squared plus the constant. But at x equals 0, y is equal to 5, and this is equal to c. So c is equal to 5. So this is the general solution of this differential equation. And the particular solution that satisfies this initial condition is f of x equals this should be a cubed, 1/3 x cubed plus 5. So this is the particular solution of the differential equation that satisfies the initial condition. Okay. What's called a differential equation for growth and decay is where dy dx, the rate of change of your function, is proportional to y, is c times y for some constant c. And the general, I shouldn't call this c, perhaps, let me call it a times y. And the general solution would be y equals Well, one particular solution would be e to the a times x. And you can multiply that by any constant c for any c. And why is this a solution? Well, check. dy dx is the derivative with respect to x of c e to the ax. When you differentiate e to the ax, you get an a e to the ax. So this is ac e to the ax. This is y, so this is a times y. So for this very simple but extremely important differential equation, the general solution is this. And if you want a solution that satisfies a certain initial condition, like you want a solution y is some function f of x with, let's say, f of 0 equal to 5, then if we take a solution f of x equals c e to the ax, and you plug in x equals 0, f of 0, that's supposed to be 5, but this is then c e to the a times 0. E to the 0 is 1 is c, so c is equal to 5. So the particular solution of this differential equation satisfying the initial condition f of 0 equals 5 is, so our particular solution is f of x equals 5 e to the ax. And in fact, it's not too hard to show that this is the only solution. It's not just a solution, but it is the solution. In Calc 2, the main technique that you learned for solving an ordinary differential equation was something called separation of variables. So you have some dy dx is some function of x and y, but it might happen that you can write f of x, y as a product of, let's say, some function of x times some function of y. And then you can bring this function of y over to the left-hand side, 1 over h of y dy dx equals g of x. And then if you integrate with respect to x, what we really have over here, it's almost like these cancel. We get the integral of 1 over h of y dy equals the integral of g of x dx. And you calculate these integrals. If you can calculate these integrals, then you in fact get a solution of the equation. So let's go back and look at some examples of this. So all of these come from first-year calculus. You have the equation that say x squared plus 4 dy dx equals x times y. And I want to separate variables. That means I want to get all the y's on one side of the equation and all the x's on the other. So I can bring this y over here, 1 over y dy dx equals x over x squared plus 4. I divided by y times x squared plus 4. And now on this side, I have no y's, and on this side, I just have I just have x's. Here, I just have a y. If you like, you can think of this as if you can multiply by dx. You get 1 over y dy is x over x squared plus 4 dx. And then you integrate. The integral of 1 over y dy is the log and the absolute value of y. And to integrate this by multiply and divide by 2, then this is 1/2, and just making a substitution, u equal to x squared plus 4, this becomes the log of x squared plus 4. And 1/2 times the log is the log of the square root. So this says that the absolute value of y is, plus a constant, is when I exponentiate, I get y is equal to c times the square root of x squared plus 4. And just write y because c can be positive or negative. So this is the technique of separation of variables in ordinary differential equations. Now, what you will find in partial differential equations is sometimes the way you solve an equation is to eliminate a variable and reduce it to an ordinary differential equation, which you can solve by an elementary technique such as separation of variables. Okay. Are there any questions about this? This is, again, this is all officially review. Okay. There's one other technique for solving an ordinary differential equation, which is very nice. And it works when you have a second order linear ordinary differential equation with constant coefficients. So if you're going to have a second order linear differential equation, it's going to be of the form as follows. It will have the function u, the first derivative of u, and the second derivative of u. And linear means the coefficients don't involve u, they're just functions of x. Let's say it's homogeneous, equals 0. And constant coefficients means a, b, c are constant, they're not functions. And we want to solve this equation. So yeah, let me just make a concrete example. Suppose we have something like uxx plus 5u sub x, or maybe make it minus 5, more interesting, plus 6u equals 0. So we want to find a function which solves this equation. And functions that people like, elementary functions, are, for example, exponential functions. So let's say we try a function u equal e to the some constant times x, e to the ax. So if u is e to the ax, the derivative is a e to the ax. And the second derivative is a squared e to the ax. Now, if you plug this into the equation, what do you get? This is not an equal sign. It's a squared times e to the ax. You get a squared e to the ax minus 5 a e to the ax plus 6e to the ax equals 0. So is there a number a that satisfies this equation? I can factor in e to the ex out, e to the ax out. I get e to the ax times a squared minus 5a plus 6 equals 0. But e to the ax is never 0. The exponential function is always positive, so we can divide by it. So a has to satisfy this quadratic equation. And we can solve this equation because it factors. So a is equal to 2 or a is equal to 3. So we get two solutions to our differential equation. Let's say u1 of x is e to the 2x, and u2 of x is e to the 3x. Right? I claim these are also both solutions to this equation. Let's just check. If u1 is e to the 2x, when I differentiate once, I get 2e to the 2x. And when I differentiate a second time, I get 4e to the 2x. So if I take, this is uxx and this is ux, right? So if I take uxx minus 5ux plus 6u, that's 4e to the 2x minus 5 times 2e to the 2x plus 6 times 1e to the 2x. 4 minus 10 plus 6 is 0. So this is a solution. And similarly, if you check, this is also a solution. And in fact, for a linear equation, if you take any linear combination of these two functions, c1 e to the 2x plus c2 e to the 3x, this will be a solution for any constant c1 and c2. And in fact, you can check that every solution of this differential equation is of this form. So these are the three facts essentially from calculus, but that you have to know about ordinary differential equations. The first is how to solve an exponential growth or decay equation when you have dy dx as a constant times y. The second is the technique of separation of variables, and which is for a first order equation. And when you have a second order equation with constant coefficients and homogeneous, then you can plug in e to the ax and and you end up with the quadratic equation to solve for a, and this will give you the solutions. Are there any questions about this so far? All right, so actually, this is all I'm going to do today. But what you should do is, first of all, have the textbook. I will be supplementing the book with some additional readings that I will post on Blackboard. There are different ways to approach the subject of partial differential equations. The importance comes from the fact that whenever you try to understand anything in science, in chemistry or in physics, especially in physics, your analysis always comes down to expressing your physical problem in terms of a partial differential equation. And it's the solutions of the partial differential equation that explain what's happening in the world, what's happening in the physics. And I chose this book as kind of an experiment, but the focus of this book is to try to teach not just how to solve a differential equation, but to understand how the analysis of physical problems leads to a differential equation, so that you know why the solution of the differential equation actually tells you something about the physical world. So I really encourage you to spend a lot of time looking at the book. It's short. So each lesson is just 4 or 5 or 6 pages. But in each of the lessons, even though they're short, there's a lot to think about. So lesson 1 is really what I spent the first part of this class doing. It's the classification of partial differential equations. The number of variables, the order of the equation, linear and nonlinear equations, homogeneous and non-homogeneous equations, equations with sometimes variable and sometimes constant coefficients, and for second order linear partial differential equations in 2 variables, the classification in terms of hyperbolic, elliptic, and parabolic. Okay. So I would show you a picture of the textbook, but I don't have it here where I am. I bought mine from Amazon. Go to Amazon, there's only one. It costs it's less than $20, but there's only one. I mean, there's no option. There's no like choice of books. There's one book by this guy with the title. It's called Partial Differential Equations for, I think, for engineers and scientists. It's listed on the instruction sheet on Blackboard, and I also emailed it to you. And it's a paperback, and that's what you get. There's no ambiguity. Starting next week, I will have office hours immediately after class on Monday and Wednesday, starting at 1 o'clock. And it has a separate Zoom address, which I've sent to you. And that's a place where you can ask me to do problems. But also, at the beginning of every class, I will start by asking if there are any questions. And I'm happy to spend the beginning of every lecture class answering questions. Okay. Are there questions about it? Anything else? Okay, well, if not, then we will stop for the day, and I will be back Monday morning at 11 o'clock. The homeworks aren't posted on Blackboard. The homework, sorry, let me repeat that. So the homeworks from the book are in the book. I will be supplementing that with additional homework problems, and those will be posted on Blackboard, and I will also generally email them out to you. Someone's asking about complex numbers. By the time you get to a 400 level math class, I assume you know the complex numbers. If not, you should, look them up somewhere. And if you have questions about anything, you can ask me during office hours. That's fine. But it's certainly expected that you know complex numbers. So you are expected to know whatever are the prerequisites for the class, which certainly includes pre-calculus and calculus and complex numbers you have to have seen by the time you get to a 400 level math class. They're just like numbers, that's all. They're nice numbers. Okay, if there's nothing else, everybody have a good weekend. Bye.